Hello, dreamer. Wherever you are right now, curled in a cocoon of blankets, sinking into your favorite couch, or stealing a quiet moment in a dimly lit room, welcome to Hafee Sleep. This is your sanctuary, a place where chaos softens, thoughts unwind, and the weight of the world dissolves into calm. I'm so glad you're here. Before we drift into tonight's journey among the stars or sink into deep relaxation, do something kind for your future self. Tap that subscribe button. It's like reserving your favorite pillow every time you need escape. And if this space brings you peace, gently tap like too. It helps others find their way here. Now, tell me softly in the comments, where are you resting tonight? The city? The mountains? Somewhere rain whispers against the window? I read everyone. Your stories make this corner of the cosmos feel like home. Let go of everything else now and just breathe. This is Hafee Sleep, and tonight we explore the serene, silent majesty of black holes. Picture this, if you will, the ultimate retirement community. Not some sunny beachfront property, mind you, but a vast velvet black expanse sprinkled with diamond-like stars. And drifting through this cosmic quiet, like the most serene, albeit slightly greedy, pensioners you could imagine, are the black holes. Yes, those terrifying monsters of popular sci-fi. Out here in the real universe, they're often just chilling. Well, as much as an object with gravity so strong not even light can escape can be said to chill. Their story, from fiery birth to quiet, profound existence, is one of the universe's most astonishing tales. So grab your imaginary space blanket, lean back, and let's unravel the surprisingly calm life of these enigmatic cosmic giants, piece by fascinating piece. So, we've set the stage. The vast, quiet retirement community of space, dotted with serene black holes. But how do these cosmic retirees get their gold watch, so to speak? How does a vibrant, shining star transform into the universe's ultimate introvert? It all begins, not with a whimper, but with the most spectacular fireworks display imaginable, the death throes of a truly massive star. Forget our gentle sun. We're talking about stellar titans, the heavyweights of the cosmic gym, stars tipping the scales at 10, 20, 50 times the mass of our own familiar day star. Their journey from luminous beacon to gravitational singularity is a saga of relentless pressure, dwindling fuel, and a final, catastrophic surrender. Buckle up, because we're diving deep into the life, struggles, and ultimate transformation of one of these colossal beasts. Imagine our star, let's call it Titanica for fun. Born in a dense, swirling nebula, a stellar nursery, Titanica started life as a vast cloud of gas, mostly hydrogen, collapsing under its own gravity. From the get-go, it was destined for drama. Its immense mass meant its core got squeezed much harder and heated up much faster than a smaller star like our sun. Think of it like inflating a balloon. If you blow really hard right away, the pressure inside skyrockets instantly. That's Titanica's core. Now, inside this furious, superheated core, millions of degrees hot, something incredible, yet fundamental, happens. Nuclear fusion ignites. This is the star's engine, its reason for shining. Hydrogen atoms, the simplest and most abundant building blocks in the universe, are moving incredibly fast due to the heat. They slam into each other with such force that they overcome their natural repulsion, like trying to force the same poles of two magnets together. When conditions are just right, the heat and pressure intense enough, they actually stick together, or fuse. But one hydrogen atom, just a proton, fusing with another hydrogen atom, another proton, doesn't quite work directly. It's a bit more complex, involving steps where protons turn into neutrons via the weak nuclear force, but the net result is this: 4 hydrogen nuclei, protons, ultimately combine to form one helium nucleus, 2 protons and 2 neutrons tightly bound. Here's the magic trick. The mass of that single helium nucleus is ever so slightly less than the mass of the 4 separate protons that made it. Where did that tiny bit of mass go? Albert Einstein's famous equation, EMC2, tells us mass and energy are interchangeable. That missing mass has been transformed into pure, raw energy, an enormous amount of energy. It's like taking a few specks of dust and converting them entirely into the blast of a nuclear bomb. This energy radiates outward from the core in the form of photons, particles of light, and also as neutrinos, ghostly particles that barely interact with anything. The outward rush of this energy creates a powerful pressure, pushing relentlessly outward against the star's own immense gravity, which is trying to crush everything inward. This is the cosmic tug-of-war we mentioned earlier. For Titanica, this balance is maintained for millions, sometimes even billions, of years. It's a stable, albeit incredibly violent, equilibrium deep within its core. The star shines brightly, fiercely, bathing any hypothetical planets in intense radiation. This phase, where a star fuses hydrogen into helium in its core, is called the main sequence. Our sun is happily and stably chugging along in its main sequence phase right now. But Titanica, being a massive beast, burns through its hydrogen fuel at a prodigious, almost wasteful rate. A bigger engine burns more fuel faster. While our sun will take roughly 10 billion years to use up its core hydrogen, Titanica might guzzle its entire core hydrogen supply in just 10 million years, 1,000 times faster. It's like comparing a fuel-efficient hybrid car to a drag racer guzzling nitromethane. Eventually, inevitably, the party in the core starts to wind down. The hydrogen fuel begins to run low. Imagine the core as a giant furnace. The coal, hydrogen, is running out. As the hydrogen fusion rate slows, the outward pressure it generates weakens. Gravity, that patient, relentless force that's been held at bay all this time, senses an opportunity. It starts to win a little ground. The core begins to contract under its own weight, getting squeezed tighter. But here's the fascinating thing. Squeezing the core makes it hotter. Much hotter. Think about pumping up a bicycle tire. The pump gets warm because you're compressing the air inside, increasing its temperature. The same principle applies, magnified to stellar scales. As Titanica's core contracts, its temperature skyrockets from millions to hundreds of millions of degrees. This intense fresh heat does something crucial. It ignites the ash of the previous fusion stage. The core is now rich in helium, the product of hydrogen fusion. When the core gets hot enough, we're talking scorching temperatures around 100 million degrees Celsius. The helium atoms themselves start to fuse. Helium nuclei, also called alpha particles, slam together. But helium is a bit more finicky than hydrogen. It takes 3 helium nuclei to fuse into 1 carbon nucleus. This process, called the triple alpha process, releases even more energy per fusion event than hydrogen fusion did. It's like switching from coal to natural gas in our furnace. A hotter, more intense burn. Titanica responds dramatically to this new energy source. The outer layers of the star, which had been cooling and shrinking slightly as the core hydrogen ran low, now get blasted by this surge of new energy from the helium-burning core. They expand enormously, pushing outward against gravity with renewed vigor, the star swells up to become a red supergiant. If Titanica were in our solar system, its outer layers might engulf Mercury, Venus, Earth, and even Mars. Its surface cools down, turning a deep red, but its total brightness increases massively because of its sheer size. Think of a colossal, luminous red-hot balloon. Betelgeuse, the bright red star in Orion's shoulder, is a prime example of a star in this phase. Meanwhile, deep within the core, the helium fusion rages. But helium, too, is finite fuel. Titanica, with its enormous appetite, consumes this helium even faster than it did the hydrogen. Perhaps in only 1,000,000 years, the core helium is depleted. The music stops again. The outward pressure from helium fusion falters. Gravity, sensing another weakening, pushes back in. The core contracts once more, heating up even further under the immense pressure. Temperatures now soar to astonishing levels, around 600 million degrees Celsius. This incredible heat unlocks the next fuel, carbon. The carbon nuclei produced by helium fusion are now squeezed and slammed together at these blistering temperatures. Carbon fuses into heavier elements, neon, sodium, and even some oxygen. Each fusion step releases energy, maintaining the outward pressure against gravity, but only for a while. The star is now layered like an onion. At the very center, the hottest, densest region, carbon is fusing. Surrounding that is a shell where leftover helium is still fusing into carbon. Surrounding that is a shell where leftover hydrogen is fusing into helium. And the vast, cool, puffy outer envelope just hangs out, blissfully unaware of the frantic fusion factory deep within. This cycle becomes Titanica's desperate rhythm. Run out of fuel in the core. Core contracts under gravity. Core heats up enormously, ignites the next heavier fuel. New fusion provides outward pressure. Stability resumes, briefly. Run out of that fuel. Repeat. Each cycle happens faster than the last because the heavier elements require exponentially higher temperatures and pressures to fuse, and the energy yields per fusion event decrease. It's a star living on borrowed time, burning through its reserves at an ever-accelerating pace. Oxygen fusion ignites next at temperatures exceeding 1,000,000,000 degrees, producing silicon and sulfur. Silicon fusion follows at temperatures pushing 3,000,000,000 degrees, creating a whole slew of heavier elements, all the way up to iron. Each step is a frantic race against gravity, each fuel source more stubborn and less rewarding than the last. The core becomes a frantic, multi-layered fusion reactor, churning out increasingly heavy elements under conditions of unimaginable pressure and heat. This is where the elements crucial for planets, and indeed life itself, oxygen, carbon, neon, magnesium, silicon, sulfur, are forged in the star's final, fiery days. And then, Titanica hits the wall, iron. Iron, specifically iron-56, is the most stable, tightly bound nucleus in the universe. Fusing iron atoms together doesn't release energy, it absorbs it. It's the ultimate energy sink. It's like trying to keep a fire going by throwing on blocks of ice. Up until now, every fusion reaction released energy that helped hold gravity back. Iron fusion consumes it. This is the cosmic dead end. For a while, Titanica's silicon-burning core churns out iron, accumulating it like ash in the furnace. But this iron ash doesn't burn. It just sits there. The core is still generating energy from silicon fusion around the growing iron ball at its center. But the iron core itself is inert. As more silicon fuses into iron, the iron core grows larger and heavier. It's a ticking time bomb. Eventually, the iron core becomes so massive that even the incredible heat and pressure from the ongoing silicon fusion in the surrounding shell can't support it against its own gravity. The core's weight is simply too much. It crosses a critical threshold. The Chandrasekhar limit for degenerate matter doesn't directly apply here because the core isn't yet electron degenerate, but the principle of overwhelming gravity does. The core implodes. This isn't a slow sag. This is a catastrophic, near instantaneous collapse. We're talking about the mass of 1.5 to 3 suns, or more, imploding at velocities reaching 1/4 of the speed of light. In less than a second, the core collapses from something roughly the size of Earth down to the size of a city, and then keeps going. The collapse is so fast, so violent, that it triggers several profound events simultaneously. As the core density skyrockets, electrons, which normally provide crucial pressure by their motion, electron degeneracy pressure, are literally crushed into protons. This turns protons into neutrons and releases a flood of ghostly neutrinos. The core becomes a seething ocean of neutrons. For a split second, the collapse might be halted by neutron degeneracy pressure. Imagine trying to pack marbles into a suitcase. Eventually, they resist because they simply can't be squeezed closer together without breaking. Neutrons have a similar limit. If the core mass is below about 2 to 3 solar masses, this pressure can halt the collapse, forming a neutron star, an object so dense that a sugar cube-sized piece would weigh as much as Mount Everest. But for Titanica, our massive star, the core mass is too great. The force of gravity overwhelms even the fierce resistance of packed neutrons. The rebound, shockwave. The core collapse doesn't just stop abruptly when it hits the neutron density limit. It overshoots, bounces back slightly. This sudden halt and rebound, combined with the unimaginable pressure and the intense flood of neutrinos pouring out, carrying away the gravitational energy of collapse, creates a titanic shockwave. This shockwave blasts outward through the still collapsing outer layers of the star. Supernova. That outward-bound shockwave, amplified by the neutrino energy deposition, like a bomb getting an extra kick of explosive, rips through the star's outer layers at incredible speed. It heats the material to billions of degrees, causing runaway nuclear reactions that weren't possible before. In a blinding flash of light that can briefly outshine an entire galaxy, the star explodes. This is a core collapse supernova, type 2, or iboic, depending on the star's outer hydrogen-helium layers. The outer layers are blasted into space at thousands of kilometers per second, carrying with them the newly forged heavy elements: carbon, oxygen, silicon, iron, gold, uranium, scattering them across the interstellar medium. This enriched gas will eventually form new stars, planets, and perhaps even life. But what of the core? While the outer layers are exploding outward in a dazzling spectacle, the core's fate is sealed. Gravity, finally triumphant after millions of years of struggle, wins completely. There is no force left in the known universe that can stop the collapse of this ultra-dense, neutron-rich ball. It keeps collapsing. It collapses past the point where neutrons can hold it up. It collapses past any known state of matter. The matter is crushed beyond recognition. Atoms, protons, neutrons themselves may break down. It collapses down to a point of infinite density, a singularity. The laws of physics, as we currently understand them, Einstein's general relativity, break down here. We simply don't know what happens at the very center. Surrounding this unfathomable singularity, the point of no return is established: the event horizon. This isn't a physical surface you could touch. It's a boundary in space-time, a mathematical surface defined by gravity's ultimate victory. At the event horizon, the escape velocity, the speed you'd need to achieve to break free from the gravitational pull, equals the speed of light. Since nothing can travel faster than light, nothing, not even light itself, can escape once it crosses this boundary. Space-time is warped so severely that all paths lead inexorably inward towards the singularity. In that instant, amidst the violent death throes of the supernova explosion that scatters the star's guts across light years, the core completes its transformation. The raging fusion furnace, the red supergiant, the layered onion of nuclear burning, it's gone. In its place, born from the ashes of cosmic violence, is a region of pure, silent gravity, a stellar mass black hole. Its dramatic, explosive birth is over. Now it settles into its new existence, a profound pocket of warped space-time, drifting calmly in the cosmic dark, its event horizon marking the boundary between the universe we know and the ultimate gravitational mystery within. The titanic struggle has ended, replaced by the serene, inescapable dominance of gravity. The calm life begins. So, we've witnessed the spectacular, supernova-laden retirement party, the moment a massive star trades its fiery robes for the profound, dark cloak of a black hole. Now, settled into its new existence, our cosmic retiree isn't pacing its celestial cage, ravenously devouring everything in sight like some interstellar Pac-Man. Far from it. Picture it more like a grand, albeit slightly aloof, concierge residing in the most exclusive, gravity-warped penthouse suite in the universe. Its primary occupation? Simply being. Its immense mass, concentrated into an unfathomably small point, the singularity, warps the very fabric of space and time around it, creating a deep, invisible well, its gravity well. This isn't a destructive force actively reaching out and grabbing things. It's more like setting up a permanent, incredibly deep divot in the cosmic trampoline. The concierge isn't chasing guests. It's the geometry of space itself around it that dictates how visitors behave. Let's revisit that trampoline metaphor because it's genuinely one of the best ways to wrap your head around gravity's curvature. Imagine space-time is indeed a vast, taut, elastic sheet. Place our black hole concierge on it, represented by that impossibly heavy bowling ball. Whoomp. The sheet dips dramatically, creating a steep, smooth funnel. Now imagine rolling a marble, representing, say, a wandering comet or a photon of light, across this sheet. If you roll it from far away with a decent speed and not aim directly at the bowling ball, it might just whiz past the dip, its path slightly bent or curved by the slope, but it escapes off the edge of the sheet. That's like a comet doing a graceful gravitational slingshot around the sun, path altered, but not captured. If you roll the marble a bit slower, or aim it closer to the slope, it might get caught in the curve, loop around the bowling ball once or twice, like a planet orbiting a star, and then, depending on its speed and trajectory, either escape or settle into a stable orbit. But if you roll it too slowly, near the steepest part of the dip, or aim it directly at the center, whoosh, down it spirals, inevitably drawn towards the bowling ball. That's the fate of anything that gets too close to the black hole's event horizon with insufficient sideways speed. The crucial upgrade here is that this isn't happening on a flat 2D trampoline. Our universe has 3 dimensions of space, plus time is intimately woven into the mix. Thanks, Einstein. The black hole's gravity well is a 3D funnel. Stars, planets, gas clouds, even beams of light traveling through this region don't move in straight lines. Their paths are curved by the warped space. Light, which always takes the shortest path between 2 points, a geodesic, finds that the shortest path near a black hole is bent around the gravity well. This is why we see gravitational lensing, the distorted or multiplied images of background galaxies when their light passes near a massive foreground object like a black hole. It's not magic. It's just space itself being curved, forcing the light to follow the contours of the dip. Most stuff passing by a lone black hole out in the galactic boonies experiences this gentle deflection. It might get a cosmic speed boost or a change in direction, but it sails on its way, perhaps a little wiser about cosmic topography. The concierge notes its passage with gravitational grace, but doesn't impede its journey. Only the exceedingly unlucky or the deliberately aimed plummet down the well past the point of no return. But even the most serene concierge needs to eat. Enter the gobbling phase, though graceful cosmic dining is perhaps a more fitting term. Think of it less like a shark attack and more like a very slow, very elegant, multi-course meal at a Michelin-starred restaurant where gravity is the sommelier. Imagine our black hole retiree isn't entirely alone. Maybe before its dramatic supernova exit, it was part of a binary star system. 2 stars gracefully waltzing around their common center of mass. When the massive star exploded and left behind a black hole, the companion star might have survived, depending on the explosion's violence and distance. Now, instead of 2 stars, we have a star and a black hole locked in their gravitational dance. This companion star becomes the black hole's primary dinner reservation. The star, blissfully shining away, has an outer atmosphere. The black hole's immense gravity exerts a stronger pull on the side of the star facing it than on the far side. This difference in pull stretches the star slightly, like a cosmic version of how the moon stretches Earth's oceans to create tides. If the stars are close enough, this tidal force can become so strong that it literally pulls material, gas from the star's outer layers, away from the companion star. It's like the black hole gently tugging on the star's cosmic tablecloth, pulling wisps of stellar gas towards itself. This stolen gas doesn't fall straight down the gravity well like a stone down a well. Remember the trampoline? And remember that the star and black hole are orbiting each other? The gas stolen from the companion star has angular momentum. It was orbiting with the star. As it gets pulled towards the black hole, this sideways motion prevents it from falling radially inward. Instead, it starts to swirl around. The black hole, like water circling a drain. Sometimes, a dense cloud of interstellar gas and dust, a cosmic meatball drifting through the galactic soup, might wander too close to our black hole concierge's gravity well. The outer fringes of the cloud feel the pull, get stretched, and stream towards the black hole. Again, random motions within the cloud mean this infalling material has some inherent swirl. As it approaches the black hole, conservation of angular momentum takes over. Just like an ice skater pulling their arms in spins faster, as the gas gets closer to the black hole, its inward spiral tightens and its speed increases dramatically. This swirling material doesn't form a uniform sphere. Collisions and friction within the gas cause it to flatten out into a thin, incredibly hot, incredibly fast-rotating disk encircling the black hole's equator, the SAR accretion disk. This disk is where the black hole's otherwise calm life gets its only real splash of vibrant and incredibly violent color. It's the cosmic kitchen where gravitational potential energy gets converted into light and heat on a truly mind-boggling scale. Imagine a gigantic supercharged version of Saturn's rings, but made of searing plasma, ionized gas, atoms ripped apart into electrons and nuclei, and spinning at a significant fraction of the speed of light near the inner edge. Here's the physics buffet. Material enters the disk in the outer, cooler regions. As it gradually loses angular momentum through friction and magnetic forces, more on that soon, it spirals inward towards the hungry black hole. Conservation of angular momentum means that as it moves closer to the center, its orbital speed must increase dramatically. Think of the ice skater again. Arms out, slow spin, arms in, fast spin. Near the event horizon, orbital speeds can be half the speed of light or more. That's orbiting an object hundreds of thousands of times per second. As the gas spirals inward, it gets packed into a smaller and smaller volume. Imagine billions of tons of gas being forced into an ever narrower, faster spinning chute. This compression is immense, but the real heat generator is friction. Not simple rubbing like your hands, but a complex dance involving magnetic fields and turbulent eddies within the plasma. Atoms, ions, and electrons moving at these insane speeds in different orbits and layers constantly collide and interact. This viscosity, a kind of internal friction in the fluid disk, converts their kinetic energy, the energy of motion, into thermal energy, heat. Lots of heat. The temperatures reached in the inner accretion disk are beyond terrestrial comprehension. We're talking millions of degrees in the outer parts, soaring to billions of degrees near the event horizon. At a few million degrees, matter glows fiercely in ultraviolet light. At tens of millions, it emits X-rays. At hundreds of millions to billions of degrees, it's a torrent of high-energy X-rays and gamma rays, the most energetic forms of light. This isn't the gentle glow of a candle or even the fierce light of the sun. It's a screaming torrent of radiation generated by the sheer violence of matter being compressed, accelerated, and shredded by tidal forces and friction as it plummets towards oblivion. This is the primary way we detect stellar mass black holes. They announce their feeding time by becoming the brightest X-ray sources in the sky, visible across thousands of light years. They are cosmic lighthouses, but instead of a rotating beam, they emit a constant, deafening, to X-ray telescopes, scream born of gravitational fury. Material gradually works its way inward through the disk, shedding angular momentum and gaining speed and heat. Eventually, it reaches the innermost stable circular orbit, ISCO. Inside this point, stable orbits are impossible according to general relativity. Material must plunge almost radially inward towards the event horizon. There might be a final, incredibly hot and thin plunging region, but it happens incredibly fast. Then, it crosses the event horizon, and from the perspective of the outside universe, it vanishes. Poof, gone. The intense light, the searing heat, the frantic motion, all cut off abruptly at that invisible boundary. The matter adds its mass to the black hole, making the gravity well infinitesimally deeper, and its information, as far as we currently understand, is lost to our universe. It's the ultimate cosmic disappearing act. The meal is consumed, and the calm returns. It's a slow, steady accretion process, a celestial whale leisurely filtering krill from the ocean, not a frenzied shark tearing into a seal. But wait, there's more on the menu. Sometimes this swirling feast in the accretion disk gets a little messy. Not messy for the black hole itself. It remains pristine within its event horizon, but messy in the disk's dynamics. Powerful magnetic fields are frozen into the superhot, ionized plasma of the disk, like threads woven through the fabric. As the disk material swirls at different speeds at different radii, inner parts faster, outer parts slower, these magnetic field lines get stretched, twisted, and wound up tighter and tighter, like rubber bands being twisted. This twisting stores enormous energy. Eventually, something has to give. The magnetic fields can snap and reconnect in explosive events, similar to solar flares but on a vastly more energetic scale. More importantly, this wound-up magnetic field can act like an escape route and a particle accelerator. Some of the infalling material, along with torrents of high-energy particles generated in the disk's inferno, gets caught in these powerful magnetic fields. Instead of spiraling all the way down into the black hole, this material gets channeled, focused, and blasted outwards along the black hole's rotational axis, perpendicular to the plane of the accretion disk. These are the prener relativistic jets. Imagine two incredibly powerful, ultra-focused fire hoses shooting out from the north and south poles of the black hole accretion disk system. But these aren't hoses of water. They're beams of plasma and radiation moving at speeds very close to the speed of light, hence relativistic. The magnetic fields act like the nozzle, collimating the jet, keeping it incredibly narrow and focused over mind-boggling distances. These jets can punch through the surrounding interstellar gas and even escape their host galaxy, stretching for thousands, sometimes millions, of light years into intergalactic space. They glow across the electromagnetic spectrum, from radio waves up to gamma rays, often outshining the entire host galaxy when the black hole is actively feeding. From our perspective, these jets are spectacular energetic signatures of a black hole's feeding frenzy. They shape galaxies, heat the intergalactic medium, and accelerate particles to energies far beyond anything achievable on Earth. But remember our black hole concierge? From its perspective, nestled serenely within its event horizon, this is just a minor side effect of the messy dining happening outside its door. The jets aren't powered by anything coming out of the black hole. That's impossible. They are powered purely by the gravitational energy released by the material in the accretion disk as it spirals inwards before it crosses the event horizon. Some of that vast energy, instead of being converted solely into heat and radiation within the disk, is tapped by the twisted magnetic fields and used to launch and accelerate the jets. It's the gravitational energy of the falling material being converted into directed kinetic energy and radiation in the jets. The black hole itself just sits there, its gravity providing the ultimate power source, while the magnetic fields act as the masterful engineers directing the exhaust. It's not a violent eruption from the black hole. It's more like the black hole's intense gravity causing the infalling material to generate powerful magnetic winds that blow some material away at incredible speeds. A gentle, albeit incredibly powerful, gravitational burp. So, the calm life of our black hole retiree? It's a life defined by profound gravitational presence. Most of the time, it's the serene architect of space-time curvature, subtly guiding the paths of passing stars and light. Occasionally, it hosts a slow, majestic feast, drawing in material that swirls in a brilliant, violent disk of doomed plasma, powering cosmic beacons of X-rays and gamma rays. And sometimes, that feast gets energetic enough to generate magnetic fireworks, launching jets that pierce the darkness of intergalactic space. But through it all, the black hole itself remains the calm center, the silent singularity, the ultimate endpoint. The messy, energetic, luminous drama all unfolds outside, the event horizon, powered by gravity, shaped by angular momentum and magnetism. Within the horizon, only gravity's final, inescapable whisper. The concierge presides, warping space, consuming matter, and occasionally lighting up the cosmos, all from the quiet depths of its eternal gravity well. It's a calm life, punctuated by moments of breathtaking gravitational theater, all orchestrated by the simple, profound act of matter surrendering to the deepest well in the universe. So, we've explored the surprisingly serene existence of our black hole retiree, its gravity well gently warping the cosmic neighborhood, and the occasional elegant, if violently luminous, dining experience courtesy of an accretion disk. But now comes the million-dollar question, the one that's tickled human imagination since these cosmic oddballs were first theorized. What does it actually look like? Stare out into the night sky, point your trusty telescope, and, well, good luck. By their very nature, black holes are the ultimate cosmic ninjas. They don't emit light. They don't reflect light. They are profound voids, regions of space-time, where gravity has slammed the door shut on the photon express. Seeing nothing isn't exactly a helpful observation report. It's like trying to describe the shape of a hole by only looking at the dirt around it. But fear not. While we can't see the black hole itself, we are master cosmic detectives, skilled at observing the profound effects it has on its surroundings. We paint its portrait not with light it emits, but with the light it bends, blocks, and inspires. Method 1. The glowing hula hoop of doom, the accretion disk. The most obvious, and often the most spectacular way we see a black hole is when it's actively dining. Remember that vast, flat, superheated whirlpool of gas and plasma we call the accretion disk? When present, it's like someone switched on a cosmic neon sign pointing straight at the invisible monster at its center. Imagine a gigantic incandescent donut. The hole in the middle? That's roughly where the event horizon lurks. The donut itself? That's the accretion disk, blazing with the furious energy of doomed matter. But it's not a uniform glow. Think of it more like a multi-ringed circus of light, each ring hotter and brighter than the last as you move inward towards the abyss. Outer rings. Farther out, where material is just beginning its death spiral, temperatures might be a relatively cool few thousand degrees, still hot enough to melt any known material instantly. This region glows fiercely in infrared and visible light, a deep, sullen red or orange, like the dying embers of a colossal campfire. If our black hole has a companion star, it's siphoning gas from, telescopes might see this star seemingly embedded in a swirling, glowing nebula of stolen atmosphere. Middle rings. As the material spirals inwards, squeezed tighter and moving faster, friction and compression heat it to millions of degrees. Now, it's not just glowing, it's screaming in ultraviolet light. This is the realm of searing blue-white brilliance, far more intense than the hottest O-type stars. Space telescopes like Hubble can pick up this fierce UV glare. Inner rings, plunging region. This is where things get truly apocalyptic. Temperatures soar into the hundreds of millions, or even billions of degrees. At these extremes, matter doesn't just glow. It blasts out high-energy X-rays and gamma rays, the kind that penetrate lead and require specialized space telescopes like Chandra or NuSTAR to observe. This inner edge is a blur of relativistic speeds, a chaotic maelstrom just outside the point of no return. The light here is warped and twisted by the black hole's gravity itself. This accretion disk isn't just a flat circle either. Depending on our viewing angle, it can appear different. If we see it face on, It looks like a bright, compact disk with a dark center. If we see it edge-on, it might look like two bright lobes sandwiching a dark lane, the disk itself, possibly with jets spearing out perpendicularly. The presence and structure of this luminous disk, visible across multiple wavelengths, radio, infrared, visible, UV, X-ray, gamma ray, are the brightest, most unmistakable billboards advertising Black Hole Diner, open for business. It's like seeing the frantic, sparkling water swirling with incredible speed around a bathtub drain, brilliantly illuminating the drain hole itself, even though the hole is dark. The water isn't the drain, but it shows you exactly where the drain is and how powerful its pull is. For stellar mass black holes in binary systems, like the famous Cygnus X1, this intense X-ray emission is often the first clue to their presence. For supermassive black holes at galaxy centers, active galactic nuclei or AGN, the accretion disk's brilliance can outshine the entire galaxy of billions of stars. Method 2. Gravitational lensing. Now, what if our black hole retiree is taking a nap? No companion star, no gas cloud buffet, just drifting calmly through the interstellar void. No glowing disk means it's back to being an invisible phantom, right? Not entirely. Remember that deep gravity well-warping space-time? It acts like a lens made purely of gravity, bending the path of any light that passes near it. This is gravitational lensing, one of Einstein's most startling predictions, and it's our second key tool for painting the black hole's portrait. Imagine you're looking at a distant star or galaxy directly behind a black hole relative to your viewpoint. Normally, the black hole would block our view, but because of the warped space, the light from the background object doesn't travel in a straight line. As it skirts the black hole's intense gravity well, its path gets bent. Think of rolling a marble across that cosmic trampoline near the bowling ball. Its path curves. From our perspective, the light rays that would have been blocked by the black hole are bent around it. The light rays that would have passed far away are bent less. This bending creates several possible effects, depending on the alignment. Einstein ring. If the background light source, a star or galaxy, the black hole, and our telescope are lined up almost perfectly, the bending can be so symmetric that we see the background object smeared out into a complete circle of light around the black hole's location. It's a perfect, or near perfect, luminous halo centered on the invisible point of immense gravity. This is the rarest and most striking effect, a cosmic bullseye marking the black hole. While perfect rings are rare for single stars, they are more common when lensing entire galaxies. The Hubble Space Telescope has captured stunning examples of these Einstein rings caused by the gravity of massive foreground galaxy clusters, which contain dark matter and often central supermassive black holes, indirectly highlighting the black hole's gravitational role. Multiple images. More commonly, if the alignment is slightly off-center, we see multiple distinct images of the same background object arrayed around the black hole. It's like looking into a funhouse mirror that creates clones. You might see 2 or 4 distorted images of the same galaxy, forming a cross-like pattern around the central dark region where the black hole resides. The precise number, position, and brightness of these images tell astronomers a huge amount about the mass and position of the invisible lens, our black hole. It's like having multiple distorted reflections revealing the shape of an invisible object. Distortion and magnification. Even if the alignment doesn't produce distinct rings or multiple images, the background objects will still appear stretched, distorted, or magnified. A galaxy might look like a surreal, elongated arc. The gravity well acts like a magnifying glass, sometimes making distant objects appear brighter than they actually are. By meticulously mapping these distortions in the light of background stars or galaxies as they pass behind a suspected black hole region, astronomers can chart the shape and depth of the invisible gravity well, confirming the presence and estimating the mass of the black hole responsible. It's detective work using light itself as putty, stretched and molded by gravity. Method 3. The invisible puppet master, stellar orbits. Our third technique is perhaps the most direct proof of an object's extreme mass and compactness, watching stars dance around nothing. Imagine looking at the center of a crowded ballroom and seeing a small group of dancers whirling around an empty spot with frantic, almost impossible speed and precision. You wouldn't see the person they're dancing with, but you'd know someone incredibly important and massive must be standing there. That's precisely how we confirmed the supermassive black hole at the heart of our own Milky Way, Sagittarius A. The galactic center is a crowded, dusty place, but infrared telescopes which can peer through much of the obscuring dust have given us a front-row seat to an astonishing cosmic ballet. Astronomers have spent decades patiently tracking the motions of individual stars orbiting an apparently empty point near the constellation Sagittarius. Stars like the famous S02 and S0102 don't orbit in slow, stately ellipses like planets around the Sun. They whip around their unseen partner at speeds exceeding 5,000 kilometers per second. That's nearly 2% the speed of light, on incredibly tight elliptical orbits that bring them breathtakingly close to the central point. By meticulously plotting these orbits, the shape, the speed at different points, the time it takes to complete one orbit, period, astronomers can apply Newton's laws and Einstein's for the really close encounters to calculate the mass of the object the stars are orbiting. The result is mind-boggling, roughly 4 million times the mass of our Sun, packed into a region smaller than our solar system. What could possibly be that massive and that tiny? A cluster of stars? Impossible. They'd collide and merge instantly. A cluster of neutron stars? Still not dense enough, and the interactions would be catastrophic. The only known object that fits the bill, that can pack that much mass into such an incredibly small volume without immediately collapsing under its own gravity, because it already is collapsed, is a supermassive black hole. Watching these stars zip around their invisible pivot point is like seeing the black hole's immense gravity pulling the strings, making the stars trace out its signature in the fabric of space-time. It's the ultimate demonstration of an unseen force, revealing itself through its influence. Method 4. The shadow on the wall. The Event Horizon Telescope image. All the methods above are powerful indirect evidence, but in April 2019, humanity took a giant leap. We captured the first direct image, not of the black hole itself, still impossible, but of its shadow silhouetted against the glowing backdrop of its accretion disk. This monumental achievement was the work of the Event Horizon Telescope, EHT collaboration, a global network of radio telescopes spanning the globe, from Hawaii to the South Pole, working together as one Earth-sized virtual telescope. Their target? 2 supermassive black holes, Sagittarius A star at our galaxy's heart, and the even larger M87 star at the core of the giant elliptical galaxy Messier 87, 55 million light-years away. M87 star proved easier to image first due to its larger apparent size. It's much bigger, though farther away, and less variable accretion flow. After years of observations, staggering amounts of data, equivalent to all the selfies taken by 40,000 people over a lifetime. In complex computational wizardry, the image emerged, a fuzzy but unmistakable dark circle surrounded by a bright asymmetrical ring of orange-yellow light. What are we actually seeing? The bright ring. This is not the accretion disk itself, like we see in artist illustrations. It's the light from the accretion disk behind the black hole, bent by its intense gravity around the event horizon and focused towards our telescopes. Because the disk is rotating, the light on the side coming towards us, due to the Doppler effect, is boosted in brightness and blue shifted, though the image is color-coded for intensity, not actual color, while the light on the side moving away is dimmed and red shifted. This creates the characteristic asymmetric ring, brighter on one side, dimmer on the other. It's the ultimate gravitational lensing effect, wrapping the disk's light completely around the black hole's shadow. The dark center, the shadow. This dark region at the heart of the bright ring is the black hole shadow. It's larger than the event horizon itself. Why? Because the black hole's gravity bends light paths so severely that photons passing very close to the event horizon get captured or bent into orbits that never escape. The shadow represents the region where light rays aimed directly at us from behind the black hole would have to pass so close to the event horizon that they get swallowed or deflected away. It's the silhouette of the event horizon's sphere of influence against the luminous background of the lensed accretion disk light. The size of this shadow directly relates to the black hole's mass and the properties of space-time around it. Seeing this shadow was a stunning, direct confirmation of Einstein's general relativity predictions for the extreme environment around a black hole. The image of M87 Kin wasn't a sharp, high-definition picture. It was fuzzy, like a photograph taken through thick fog. But it was real. It wasn't an artist's impression. It was data transformed into vision. It showed the serene, profound presence of a supermassive black hole. Not a raging monster, but a calm, deep, gravitational pit. Its immense power silently warping the light of its surroundings into a glowing halo of confirmation. It looked exactly like theory predicted gravity's ultimate manifestation should look. The EHT continues to improve, aiming for sharper images of M87T, SGRA, and other supermassive black holes, potentially even capturing movies of the turbulent plasma swirling around the event horizon. So, what does a black hole look like? It looks like the brilliant, multicolored fury of an accretion disk swirling around an abyss. It looks like the distorted funhouse mirror images of background galaxies stretched into arcs and rings by an invisible lens. It looks like the frenzied high-speed waltz of stars orbiting an empty point with impossible mass. And most directly, it looks like a serene, dark shadow, a cosmic silhouette ringed by a fiery halo of lensed light, a profound confirmation of gravity's dominion over space and time. We don't see the singularity. We don't see the event horizon directly. But by observing the light it bends, the material it heats, the stars it whips around, and the shadow it casts, we paint a remarkably detailed portrait of this most enigmatic cosmic retiree. It's a portrait defined by absence, by distortion, by influence, and by the brilliant consequences of matter surrendering to gravity's deepest embrace. It's a portrait not of the thing itself, but of the profound hole it punches in the universe, a hole outlined by the frantic light of infalling plasma, the distorted images of distant galaxies, the frenetic orbits of captive stars, and finally, the the serene dark shadow that whispers gravity's ultimate secret. The black hole remains the unseen concierge, but the lobby of its gravity well is ablaze with the unmistakable signs of its presence. So, we've toured the surprisingly serene retirement community of black holes, witnessed their explosive birth from dying stellar titans, marveled at the elegant chaos of their accretion disk dinners, and even learned how to paint their portrait using the light they bend and the stars they steer. But now comes the big, almost philosophical question. Why? What cosmic purpose could these profound pockets of nothingness possibly serve? The universe, in its infinite wisdom, doesn't exactly hand out employee handbooks or mission statements. Galaxies don't have CEOs, stars don't file quarterly reports, and black holes certainly don't clock in for a gravity shift. Yet, as we observe the grand tapestry of the cosmos, a fascinating picture emerges. Black holes aren't just bizarre cosmic accidents or destructive dead ends. They play several crucial, even elegant roles in the universe's grand story. They are the ultimate recyclers, the unseen architects, the most extreme physics labs, and perhaps the universe's final enduring monuments. Let's unpack this cosmic why. 1. The cosmic recyclers librarians, with a dash of hoarding. Imagine the universe as a vast, dynamic recycling plant, crossed with an infinitely complex library. Stars are the primary furnaces and publishing houses. They take the simplest element, hydrogen, the cosmic blank page, and through nuclear fusion in their cores, forge heavier elements, the words, sentences, and chapters of the cosmic story. Helium, carbon, oxygen, nitrogen, iron, gold, uranium, all the elements that make up planets, oceans, mountains, and us, are cooked up inside stars. Now, when a small or medium star like our Sun dies, it's a relatively tidy affair. It puffs off its outer layers as a beautiful planetary nebula, gently returning those enriched gases, carbon, oxygen, nitrogen, back to the interstellar medium, the cosmic recycling bin and library shelves. The leftover core becomes a white dwarf, a dense, Earth-sized ember that slowly cools over billions of years. The valuable books, elements it produced, are mostly put back into circulation. But for the massive stars destined to become black holes, their exit is more like a controlled demolition combined with a vault ceiling. Their death throes, the core collapse supernova, are spectacularly messy and productive. The explosion blasts the star's outer layers, now packed with a rich cocktail of newly forged heavy elements, all the elements up to iron, plus even heavier ones created in the supernova blast itself, out into space at incredible speeds. This is the ultimate cosmic recycling act. That supernova debris mixes with existing gas clouds, enriching them with the essential ingredients for rocky planets, complex chemistry, and ultimately, life. The calcium in your bones, the iron in your blood, the oxygen you breathe. Much of it was forged in the heart of a massive star and scattered by its supernova death. We are, quite literally, star stuff, thanks to this explosive recycling. However, the core of that massive star doesn't get recycled. It doesn't gently return its mass. It collapses beyond the point of no return, forming a black hole. This is where the librarian and hoarder aspects kick in. A significant chunk of the star's original mass, often several times the mass of our Sun, is effectively removed from the active baryonic matter cycle. Baryonic matter is the normal stuff: protons, neutrons, electrons, the atoms that make up stars, gas, planets, and us. The black hole takes this matter and locks it away behind its event horizon. It's not destroyed, at least according to general relativity. The information paradox is a whole other shelf in the cosmic library we haven't fully cataloged yet. But it is taken off the active shelf. It's like the most valuable fundamental manuscripts of the cosmic library being placed into a secure, inaccessible vault. Why is this removal important? It influences the very distribution and concentration of matter in the universe over time. Galaxy evolution. By locking away mass, black holes prevent that mass from immediately forming new stars or adding to existing ones. This helps regulate the star formation rate in galaxies. If all the mass from every massive star was instantly recycled, galaxies might burn through their gas too quickly in a frenzy of star formation, blasting themselves apart with supernovae before complex structures could form. Black holes act as cosmic mass sinks, subtly modulating the flow. Matter concentration. The sheer gravitational pull of black holes, especially supermassive ones, draws matter towards them. While much of it might end up swirling in an accretion disk and eventually locked away, the process of accretion can also funnel gas into the galactic center, potentially influencing the formation of dense stellar clusters, or even helping to trigger bursts of star formation around them, not just suppress it farther out. It's a complex gravitational dance. The missing mass puzzle. While dark matter is the dominant player, the mass sequestered in stellar mass and supermassive black holes across the universe is not insignificant. It's a part of the overall cosmic budget of matter, just stored in a very different, inaccessible account. So, black holes are essential recyclers on one hand, scattering the heavy elements of life, while also being cosmic librarians and hoarders on the other, locking away fundamental mass and information, profoundly shaping the universe's matter inventory and evolution. They ensure the cosmic story has both the raw materials, scattered elements, and the structural pacing, regulated mass flow, needed for long-term complexity. 2. The galaxy architects, the silent CEOs in the center. Now let's zoom out from individual stars to the grand scale of galaxies. Almost every large galaxy we observe, including our own beloved Milky Way, harbors a secret at its very heart, a supermassive black hole. SMBH. We're not talking about the stellar mass retirees, a few to tens of solar masses anymore. These are cosmic behemoths, weighing in at millions to billions of times the mass of our Sun. Sagittarius A. In our Milky Way is a relatively modest 4 million solar masses. The one in the galaxy M87, famously imaged, is a whopping 6.5 billion solar masses. How did they get so ludicrously huge? It's an active area of research, likely a combination of gulping gas, feasting on vast amounts of gas funneled towards the galactic center during mergers or periods of instability, swallowing stars, tidally disrupting and consuming stars that wander too close, merging, colliding and combining with other black holes as galaxies themselves merge over cosmic time. Imagine two galactic cores, each with their own SMBH colliding. The black holes eventually find each other, spiral in, and merge in a cataclysmic event that shakes space-time itself, emitting gravitational waves, creating an even more massive single SMBH. The truly fascinating part isn't just their size, but their profound, seemingly counterintuitive connection to the galaxy they inhabit. Observations reveal a remarkable correlation. The mass of the central SMBH is closely linked to properties of the galaxy's bulge, the central densely packed swarm of stars. Bigger bulge, bigger central black hole. This suggests they didn't just grow independently. Their growth histories are intimately entwined over billions of years. The SMBH isn't just a passive occupant. It's a fundamental component, a silent architect. How does a black hole, a cosmic vacuum cleaner, build or shape a galaxy? Through the energetic tantrums of its youth, its active feeding phases, often seen as quasars or other types of active galactic nuclei, AGN. Picture the central SMBH as a powerful furnace, gravity, connected to a complex heating and cooling system, the galaxy's gas. When a lot of gas falls towards the center, perhaps triggered by a galaxy collision or instability, the SMBH feasts. The accretion disk blazes with incredible luminosity, outshining the entire galaxy. But crucially, it doesn't just radiate light, it also generates powerful winds, and those spectacular, relativistic jets we discussed earlier. These winds and jets act like cosmic blowtorches and pressure washers. They inject enormous energy into the surrounding gas reservoir of the galaxy. This has two major effects. The injected energy heats the galactic gas to very high temperatures. Hot gas is puffed up and less likely to collapse under its own gravity to form new stars. It's like turning up the thermostat so water won't freeze. This suppresses star formation, particularly in the central regions, but potentially galaxy-wide. In the most energetic cases, especially with powerful jets, the AGN can literally blow huge bubbles of hot gas out of the galaxy entirely, ejecting it into the surrounding intergalactic medium. This is galactic feedbacks on a grand scale. It removes the raw material, cold gas, for future star formation. Here's the elegant feedback loop. By heating and ejecting gas, the AGN effectively starves itself of future fuel. It shuts down its own feast. As the gas supply dwindles or is blown away, the accretion slows, the AGN quiets down, the galaxy cools. Gas might slowly accumulate again over time, potentially leading to another feeding frenzy later. It's a self-regulating cycle. Why is this important? Without this SMBH feedback, galaxy evolution might look very different. Runaway star formation. Galaxies might convert all their gas into stars far too quickly in a single short-lived burst, leaving behind a red and dead galaxy with no fuel for future generations of stars or planets. Monster galaxies. Galaxies might grow excessively large and massive without this regulatory pressure. Lack of diversity. The beautiful variety of galaxy shapes and sizes we see, spirals, ellipticals, irregulars, might be diminished. The central supermassive black hole, through its energetic outbursts during feeding, acts like a cosmic governor or thermostat. It prevents the galaxy from growing too big too fast, regulates the pace of star formation over cosmic time, enriches the intergalactic medium with ejected gas and metals, and contributes to the overall ecosystem of the cosmic web. A quiet SMBH, like our own Sagittarius A is today, often signifies a mature, stable galaxy that has passed through its tumultuous, star-forming youth. The silent CEO has done its job and is now overseeing a well-established domain. Their presence at the center isn't a coincidence. It's fundamental to the galaxy's very structure and life cycle. 3. Gravity's ultimate laboratory, pushing Einstein to the edge and beyond. Black holes aren't just cosmic features. They are nature's most extreme physics laboratories. They exist in a realm where gravity isn't just a force. It's the warping of the very fabric of space and time itself, as described by Einstein's theory of general relativity, GR. Studying black holes pushes GR to its absolute limits and offers tantalizing hints of physics beyond it. Testing relativity under fire. Einstein's theory has passed every test thrown at it on Earth and in the solar system with flying colors. But black holes are where GR faces its most extreme exam. The conditions near the event horizon, and especially at the singularity, involve unimaginable gravity, curvature of space-time so severe that it creates a one-way boundary, the event horizon, and a point of infinite density, the singularity. Relativistic speeds. Matter in accretion disks orbits at significant fractions of the speed of light. Time dilation. Time passes incredibly slowly for an object falling towards the event horizon compared to a distant observer. Near the singularity, time effectively loses its familiar meaning. Warped light paths. Gravitational lensing becomes extreme, bending light into rings and loops. Frame dragging. A rotating black hole, a Kerr black hole, literally drags space-time around with it, like a spinning spoon in thick honey. Observing phenomena like the precise orbits of stars around Sagittarius A star, especially the star S02, which gets incredibly close. The shape and asymmetry of the accretion disk in the EHT image of M87 star. The properties of gravitational waves from black hole mergers detected by LIGO and Virgo. All of these are stringent tests of general relativity as predictions in environments utterly unlike anything in our solar system. So far, GR has held up spectacularly well. The EHT image matched Einstein's predictions with stunning accuracy. This isn't just confirming what we know. It's exploring gravity in its most dominant and purest form. The singularity problem. The quantum conundrum. However, GR hits a brick wall at the singularity. The equations predict a point of infinite density and curvature, a place where the known laws of physics break down completely. This screams that GR, which describes the large-scale universe so well, is incomplete. It doesn't incorporate the other pillar of modern physics, quantum mechanics. QM, which governs the bizarre world of the very small. The need for quantum gravity. The singularity is a signpost pointing towards the need for a theory of quantum gravity, a framework that successfully merges general relativity and quantum mechanics. Black holes are the natural testing ground for such a theory, precisely because they concentrate so much mass, gravity, into such a tiny volume, quantum scale. The information paradox. This is perhaps the most famous puzzle at the GR-QM boundary. QM says information, the quantum state of particles, can never be truly destroyed. GR, applied to black holes, suggests that when matter falls in, all information about it, except mass, charge, and spin, is lost forever at the singularity. Hawking radiation, which we'll get to, adds fuel to the fire. Does information leak out with the radiation? Is it preserved on the event horizon somehow, the holographic principle? Or is it truly lost, violating QM? Resolving this paradox is key to understanding the fundamental nature of reality. Probing Planck scales. Conditions near the singularity are thought to involve the Planck scale. Unimaginably tiny lengths and time scales, 10 to power minus 35 meters to 10 to power minus 43 seconds, where quantum fluctuations of space-time itself are believed to become significant. Black holes offer our only potential observational window, albeit indirect, into this realm where space and time may lose their smooth, continuous nature and become foamy or discrete. Psho, the universe's final monuments and their quantum whisper. Let's cast our gaze far, far into the future. We're talking timescales that make billions of years look like the blink of an eye, trillions upon trillions of years. The universe is expanding and accelerating in that expansion due to dark energy. Galaxies beyond our local group will have faded from view, their light stretched beyond detectability. Within galaxies, star formation is a dying ember. The last generation of stars, small, frugal red dwarfs, will have finally burned through their fuel, fading to cold, dark cinders, black dwarfs. Brown dwarfs, failed stars, and the remnants of dead stars, white dwarfs, neutron stars, will litter the cooling cosmos. Planets, if any remain bound, will be frozen husks. The universe is cold, dark, and increasingly empty. This is the degenerate era. But amidst this fading twilight, some structures endure. Black holes. Stellar mass black holes, supermassive black holes, and any intermediate ones formed over the eons. Why? Because they are stable. There's no fusion process to exhaust, no internal pressure to subside. They simply are, defined only by their mass, spin, and charge, sitting in their eternal gravity wells. In this cold, dark, and vastly expanded universe, black holes become the dominant large-scale structures, the last monuments to the universe's once vibrant past. They drift through the cosmic darkness like silent, ancient monoliths. But even black holes aren't truly eternal. Enter the genius and utterly bizarre concept of Hawking radiation. Proposed by Stephen Hawking in 1974, this is where quantum mechanics reaches out and touches even the most isolated black hole, connecting it to the wider universe in a slow, inexorable decay. The quantum vacuum isn't empty. According to quantum mechanics, empty space is not truly empty. It's a seething, frothing sea of Chakram virtual particles. These are particle-antiparticle pairs, like an electron and a positron, or two photons, that spontaneously pop into existence out of the pure energy of the vacuum itself, borrowing energy from the universe thanks to the Heisenberg uncertainty principle. Normally, they annihilate each other almost instantaneously, paying back the energy loan before anyone, like the cosmic energy police, could notice. It's a constant, frantic dance of creation and destruction happening everywhere all the time. The event horizon's quantum trick. Now, imagine this happening right at the very edge of a black hole's event horizon. One of these virtual particles pops into existence just outside the horizon, while its partner pops into existence just inside. The particle inside is trapped. It must inevitably fall into the singularity. The particle outside, however, is free. From the perspective of an observer outside the black hole, it looks like the black hole just emitted a particle. This escaping particle is real. It carries energy away from the black hole. Conservation of energy demands shrinkage. To conserve energy, because that escaping particle had to get its energy from somewhere, the black hole must lose a tiny, tiny amount of mass equivalent to the energy of the escaped particle. Essentially, the black hole pays the energy loan for the virtual particle pair by sacrificing a minuscule fraction of its own mass. The trapped particle effectively has negative energy relative to infinity, reducing the black hole's mass. The slowest evaporation imaginable. This process, virtual pairs appearing near the horizon, one falling in, one escaping, happens constantly, but at an incredibly slow rate for astrophysical black holes. The rate of Hawking radiation emission, and thus the rate of mass loss, is inversely proportional to the black hole's mass. Bigger black holes are colder and emit less Hawking radiation, much less. Stellar mass black hole, 10 solar masses. The Hawking radiation temperature is a frigid 60 billionths of a degree above absolute zero. It would take an utterly unimaginable 10 to power 67 years. That's a 1 followed by 67 zeros. To evaporate. That's about 10 TP power, 57 times the current age of the universe. For context, if you scaled the current age of the universe, 13.8 billion years, to 1 second, the evaporation time for a stellar mass black hole would be roughly twice the current age of the universe. Scaled up by that same factor, it's mind-bogglingly long. Supermassive black hole, 1 billion solar masses like M87. The temperature is an even more negligible 10 to power minus 16 Kelvin. Its evaporation time is a truly cosmic 10 to power 92 years. This number is so vast it defies analogy. The universe would be unrecognizably cold and empty long, long, long before even the tiniest fraction of this time elapsed. The grand finale, in 10 to power 67 plus years. As a black hole loses mass through Hawking radiation, it actually gets hotter and emits radiation faster. So, the evaporation process accelerates as the black hole shrinks. In the final moments, when the black hole's mass becomes very small, around the Planck mass, it's theorized to vanish in a final tiny burst of particles and energy. It would be a faint quantum spark in an otherwise cold and dark cosmos. Hawking radiation's cosmic significance. Quantum connection. It shows that even the most isolated object in the universe, defined purely by gravity, is subtly connected to the quantum vacuum. No cosmic structure is truly cut off. Theoretical unification. It represents a profound, if still not fully understood, bridge between general relativity, gravity, space-time curvature, event horizons, and quantum mechanics, virtual particles, the uncertainty principle. The ultimate fate. For stellar mass and larger black holes, Hawking radiation is utterly irrelevant on any human or even galactic timescale. They will outlast all stars by countless orders of magnitude. But in the truly far future of an ever-expanding cold universe governed by dark energy, Hawking radiation ensures that even black holes, the last monuments, will eventually fade away. The universe would enter the second dark era, where only an incredibly dilute sea of photons, neutrinos, electrons, positrons, and other fundamental particles remains, spread so thin by expansion that interactions become vanishingly rare. So why do black holes exist? They exist because gravity exists, and gravity, given enough mass concentrated in a small enough volume, inevitably wins. But their significance goes far beyond being mere endpoints. They scatter the heavy elements of life while locking away fundamental mass, shaping the cosmic matter cycle and distribution. Their supermassive kin sit at the hearts of galaxies, their energetic feedback governing star formation, galaxy growth, and evolution, preventing cosmic chaos. They provide the most extreme environments to test general relativity and probe the interface with quantum mechanics, guiding us towards a deeper understanding of space, time, and reality itself. 4. The universe's final monuments. They will endure long after the stars fade, silent witnesses to the cosmos's history, slowly fading themselves via the subtle whisper of quantum mechanics in the unimaginable far future. Black holes are not cosmic mistakes. They are fundamental consequences of physics, playing vital dynamic roles in the universe's structure, evolution, and even its ultimate destiny. They are gravity's most profound expression, sculptors of galaxies, testbeds for reality, and the serene, enduring anchors in the vast cosmic ocean. Their calm existence belies the incredible power they wield and the profound mysteries they guard. They are the universe's way of exploring the ultimate limits of gravity, matter, and time itself. So, there you have it. Far from the ravenous monsters of fiction, black holes lead lives of profound, majestic calm. Born in stellar cataclysms, they settle into roles as gravity's anchors, cosmic vacuum cleaners operating at a glacial pace, silent sculptors of galaxies, and ultimate keepers of matter's deepest secrets. They drift through the cosmic dark, warping the fabric of reality around them, visible only by the absence they create and the light they bend. They challenge our understanding of space, time, and existence itself. They are the universe's most enigmatic retirees, sitting in their gravity wells, radiating quiet power, reminding us of the incredible, often serene extremes that nature can produce. They are the ultimate testament to gravity's patient, undefeated strength, not a destructive force, but a profoundly shaping one, weaving the structure of the cosmos in the deepest silence. Next time you look up at the stars, remember, hidden in that vast darkness, amidst the stellar fires, are these profound pockets of calm, these cosmic singularities, just being. The universe is far stranger and far quieter in its extremes than we often imagine. And that's the truly beautiful secret of the black hole's calm life. And so, dear traveler, as we leave the silent majesty of black holes behind, remember this: just like them, you too hold infinite calm within you, a gravity of peace no chaos can escape. If tonight's journey settled your soul, gently tap the like button. It's a ripple of stillness sent across the cosmos. And if you're new here, subscribe to Hafee Sleep. Each tap is a star you place in your own night sky, guiding you back to peace whenever you need it. Now I'd love to know, where did your cosmic journey begin tonight? Whisper to me in the comments, your city, your country, the rain on your roof. I read every story, and together, we make this universe feel a little softer. Sleep calls, but before you drift, tap the bell icon. So next time, when stars align and weariness finds you, our next journey whispers through the cosmos, straight to you. Breathe deeply now. Feel the quiet expand inside you. This is Hafee Sleep, and wherever you are, you belong here. Rest well, dream deeply. Good night.